Today's notes are on horizontal projectiles, and we'll start with an example. Here I've got an orange ball on top of a table, and I've pushed the ball and it's rolling at a constant velocity. I took this video in slow motion. The ball is going to roll off the table with a horizontal velocity only. There's no vertical component to its initial velocity. So let's watch. And the ball falls, and the shape of that arc that the ball makes is a parabola. It's half of an upside down parabola. So I'm going to move over to notability, and we're going to analyze this motion. Now, I took some measurements. I measured the height of the table, which I'm going to call delta y, which is our vertical displacement, and it's 0.92 meters. I'm going to call this 0. So when the ball falls, it changes its height in a negative direction. Let's see, what else do I know in the vertical direction? I know that delta y, again, was negative 0.92 meters. I know that the initial vertical velocity is 0. I know that the acceleration is negative 9.81 meters per second squared. So I actually have quite a bit of information. One of the things that I can figure out about the ball is I can figure out how long it was in the air. If I go back to my kinematic equations, delta x equals v naught delta t plus 1/2 a delta t squared, I'm going to apply vertical free fall. And with vertical free fall, instead of delta x, I'll call it delta y. That just indicates that the direction is vertical. V naught is 0. And instead of acceleration, I'm going to use g for negative 9.81. So I'd put in negative 0.92 equals 1/2 times negative 9.81 t squared. And then I'm going to get out my trusty calculator and solve this. So I'm going to take negative 0.92 and divide by 1/2 of 9.81 is 4.905. That's a number I use a lot, so I kind of have it in the front of my brain. Divided by 4.905. And then I've got t squared equals 0.1876. And then I take the square root. So I'll square root that, and I get 0.433. All right, so I've got the time it takes the ball to fall, the 0.92 meters. Okay, what else can we figure out here? If I zoom in on the ball landed right about there. And let's see, this is 0. I better make this a little narrower. 10, 20, 30, 40, 50, 60. This is about 65 centimeters or 0.65 meters. And I'm going to call that distance my range. Delta x, it's also called delta x, the horizontal displacement. So in the horizontal direction, what do we know? We know one thing, we know delta x. And that's really all we know. And there's really only one formula I can use for horizontal motion because the horizontal motion is constant velocity. There's no horizontal force on the ball, and therefore there's no acceleration in the horizontal direction for the ball. Conversely, for vertical motion, we have acceleration. And that acceleration is due to the force of gravity, and the acceleration is equal to negative 9.81 meters per second squared. So anyway, I have one formula that I can use for horizontal motion, and it's delta x, displacement equals velocity times time. Now, to indicate that I'm working only in the horizontal direction, I'm going to put an x on the velocity to indicate that. So the one other thing that I know is that there's one variable that can go back and forth between vertical and horizontal. Otherwise, we have to keep everything separate. The one variable that can cross between vertical and horizontal motion is time. Time is not a vector. So the time for the ball to fall is the same whether I'm looking at delta x or delta y. So I do know that delta t for the falling ball is 0.433 seconds. And therefore, I can figure out the speed of the ball. 0.65 meters equals Vx times 0.433 meters. And then I would take 0.65 divided by 0.433. Okay, and so I get that Vx is 1.50 meters per second. Oh, that's pretty cool. I got a nice clean number there. I lucked out. Okay, that's great. Let's go back and look at the graph. Actually, I got a little fancy here. I put this into video physics. I'm going to back this up. Video physics allows me to graph the motion of the ball. So I put a dot for each step in my video. And I'm going to take a look at the graphs here. This is horizontal position and vertical position. This is horizontal position only, and I really want to focus on the top graph. So again, I really want to focus on this graph. What I can see here is that the slope of this position versus time graph, the slope of that graph is going to give me the velocity. And indeed, okay, this is horizontal position. And indeed, I see a constant slope and therefore a constant velocity. And I could calculate that slope to get what the velocity actually is. Okay, now let's go back to our graphs here and let's look at the vertical position. Here we've got vertical position and vertical velocity. And again, when I look at, now let's look at the velocity time graph. Now the velocity time graph has a negative slope. And the slope of this velocity time graph is going to be acceleration. In fact, if I were to calculate this out, it should be negative 9.81 meters per second squared. Okay, back to my video physics. The next question I want to try to solve is, what is the speed with which the ball actually hits the ground? Now the ball hits the ground at an angle. So I'm going to take this and add this to my notability. So again, my question now is, what's the speed? And actually, I'm going to amend my question. What's the velocity at which the ball hits the ground? Now, this path shows me that the ball is going to hit the ground at an angle. Oops. Come on, notability. At an angle, like this. Okay? And I want to think about that final velocity of the ball for a second. It's going to have two components. It's going to have a horizontal component and a vertical component. Now the horizontal component we already know. We found it. It's 1.5 meters per second. We know that the horizontal velocity of the ball does not change. The vertical velocity of the ball does change. Could we figure it out? Let's look at what we have. We have acceleration is negative 9.81 meters per second squared. The initial velocity of the ball, initial vertical velocity of the ball is 0 meters per second. And we also have the time that the ball was in the air. We calculated 0.433 seconds. So we can solve for the final vertical velocity of the ball with a kinematic equation. And I'll plug in the values that I have, 0 plus negative 9.81 meters per second squared times 0.433 seconds. And I'll multiply that out. And I get 4.24, actually negative 4.24 meters per second. And that's correct. Now what I have is a vector. So I'm going to redraw this, but I'm going to start a little more correctly. I'm going to start by drawing the coordinate plane. This vector is in the fourth quadrant. We just figured out that to get to this point, we would go over 1.50, and we would go down negative 4.24. Oops. So it's like an XY. It is an XY. It's a coordinate. Oops. Okay. Now what I'd like to do is I would like to find the length of that vector. In other words, how long is this? And what angle does it hit the ground? At what angle does it hit the ground? So when I define angles in the coordinate plane, I started 0 degrees and measure around this way. So I'm going to find angle X and then subtract from 360 to find the proper angle. But let's find R first. To find R, I'm going to use the Pythagorean theorem. You may recall that if you have A, B, and C of a right triangle, A squared plus B squared equals C squared. Well, on the unit circle, we write it a little bit differently. The hypotenuse is R, so we say R squared equals X squared plus Y squared. So R squared equals 1.5 squared plus negative 4.24 squared, which is going to be positive after I square it. So I'm just putting it in my calculator. And I got that R is 4.50, and the units are the same. It's meters per second. So the ball hits the ground at 4.50 meters per second. That's a little bit more than just the vertical component because I added the horizontal component and I added it as a vector. Okay, now let's figure out these angles. If I want to find out angle X here, the angle below the horizontal, I would say that the tangent of X equals the opposite side over the adjacent side. So that would be 4.24 over 1.50. I don't need to worry about the negative 4.24. I'm just thinking about this right triangle. So I'm going to end up taking the inverse tangent of 4.24 over 1.50. So I'm putting it into my calculator. And I'm having a little trouble. Maybe you're ahead of me. There we go. I get 70.5 degrees. So this angle in here is 70.5 degrees. That means if I were to measure this on the unit circle, the angle would be 360 minus 70.5, which is 289 degrees, about 289.5 degrees. So there we have it. So look what we did. We developed equations for vertical and horizontal motion of a horizontal projectile, and we applied a kinematic equation to the vertical motion of a horizontal projectile. To sum up, we want to keep the horizontal and vertical motion separate. Only time can be used in both equations. In the horizontal direction, we have constant velocity, and there's only one formula that we can use with constant velocity. Displacement equals velocity times time. In the vertical direction, we have acceleration, and you can use all of the kinematic equations, but the one that comes up the most is 1/2 delta y equals 1/2 gt squared. We also, though, could apply that vertical velocity equals initial vertical velocity plus g delta t. If it's a horizontal projectile, the initial vertical velocity is 0. And also don't forget about final velocity squared equals initial velocity squared plus 2 g delta y. That's how I would write this equation when I apply it to a horizontal projectile. All right. Hope that made sense. And